Okay, we're back, and in the last lecture, I believe we left off with the beginning of chapter 5, where we had gotten up to discussion of the concept of pressure. The most important characteristic of all for gases, as I mentioned at the beginning of the chapter, is that particles in a gas have no intermolecular attractions or repulsions at all. And so there's nothing holding the gas particles back. They move around very freely at a high rate of speed. They're in constant motion. And even though they're far apart from each other relative to the size of the particles, they will eventually hit something. When they hit something, they exert a certain amount of force on what they hit. You know, think of my finger as being a gas particle, and eventually it hits something. And when I hit the paper, I exert a certain amount of force on it. Well, gas particles zipping around and hitting the walls of a container do the same thing. And so we define the concept of pressure as the total amount of force exerted by gas particles hitting on a certain unit of area of that surface. We can define units of pressure as being something like pounds per square inch, which represents force per unit of area directly, pounds of force per square inch of area. Or in the SI system, we can define it as newtons of force per square meter of area. And that is literally a force per unit of area. And that is better known as a Pascal. But in the gas laws or gas equations that we deal with, most of the time we'll actually be using other units for pressure, units that represent pressure without giving force per unit of area directly. So we have units like millimeters of mercury or torr, and atmospheres. Remember that 1 atmosphere is the average atmospheric pressure at sea level at any given moment. And 1 atmosphere is equal to a column of mercury in a barometer that is 760 millimeters tall. And 1 millimeter of mercury is also known as a torr. So 760 millimeters of mercury is also known as 760 torr. Torr is just short for the name of the guy who invented the mercury barometer. And a column of mercury that's 760 millimeters high also happens to be 29.92 inches high. So 29.92 inches is the same as 760 millimeters. 1 atmosphere is also equivalent to 14.7 pounds per square inch, which is the English sort of version of a Pascal. In pascals, it's 101,325 newtons per square meter, which is what a Pascal is. And because Pascal is a metric unit, you can also use metric prefixes with it. So 101,325 is kind of a big number. A lot of times pressures are given in units of kilopascals. So 101,325 kilopascals. There's quite likely, if you look at the sidewall and the tires on your car, you'll find the recommended pressure not only in pounds per square inch, but also in a certain number of kilopascals. And that's because that's the official SI unit of pressure. Okay, we did some unit conversions last time, but there are a couple more I wanted to show for right now. So let's say the National Weather Service says that the atmospheric pressure is 30.44 inches of mercury. And in the United States, that is probably the most common unit used for pressure in, say, weather forecasts or whatever. The National Weather Service probably gives it in that plus other units as well. So we're wondering, what is that in PSI? And that's pounds per square inch. I don't think the National Weather Service actually gives the pressure in pounds per square inch. It gives it in inches of mercury, and I think it probably also gives it in pascals, but almost certainly not in PSI. Okay, so we have our relationships here of, all of these quantities are equal to 1 atmosphere. So when you get a unit of pressure and you want to change it to some other unit, the first thing you'd probably want to do in most cases would be change it to atmospheres. So if we have 30.44 inches of mercury and we want to change it to atmospheres, we can look at the second line here. 1 atmosphere is 29.92 inches of mercury. Okay, so inches of mercury will cancel out and you'll end up with atmospheres. And let's see, we can do this all in one step, or we can stop here and write down the answer. 30.44. 30.44 divided by 29.92 is 1.017 atmospheres. And actually, I'm going to go one more space because this isn't our final answer yet. So 1.0174 atmospheres in units of PSI would be number of atmospheres times 14.7. So now you can see atmospheres cancel and we get 14.7. We get 14.955. And let's see, looking at this, 14.7 was only 3 significant figures. That's not an exact number, that is rounded off. So 14.9. And the next digit, the first digit we're dropping is a 5. So the digit before it has to go up by 1, but then the digit before that has to go up by 1 because it's a 9. So we end up with 15.0 PSI as our pressure to the correct number of significant figures. You can use mercury barometers or similar devices known as manometers to measure pressures. And in either case, you can get out the pressure in units of the length of a mercury column. And then it just depends on what units you want to measure the length of a mercury column in. So I'm not going to do this in inches of mercury because we just did an example like that. Let's see. 23.8. Okay, so suppose your pressure is 604.5 millimeters of mercury, and we want to know what that is in kilopascals. Well, again, we have the relationships of all of these different units to 1 atmosphere. So the sensible thing to do would be change 604.5 millimeters of mercury to 1 atmosphere. There's 1 atmosphere for every 760 millimeters of mercury. And so we have this divided by 760, and that's 0.7954 atmospheres. And that times, let's see, kilopascals, 101.325 kilopascals. Okay. Let's see, 80.60, and it looks like we can use 760 millimeters of mercury for 1 atmosphere. That is an exact number. So 760 here would be considered infinite in terms of significant figures. So we've got 4 here, infinite here, used 4 for the answer here. We've got 6 here. So yeah, we can use 4 for the answer, 80.60, and that's kilopascals. So 760 millimeters or torr, millimeters mercury or torr, that's considered an exact number. But 29.92 is not exact. That's in significant figures, 4 significant figures. $14.7 would be 3 significant figures, and 101.325, that would be 6 significant figures. So 760 is, and 1 for 1 atmosphere, that would be considered infinite significant figures also. And so 760, that's infinite. All right. The book goes on and describes the manometer, a device for measuring pressures in the lab. And I'm going to skip that for now because we don't really need to go into that much detail on things. The next section is 5.3, and that's about simple gas laws. It's simple in the sense that they have to do with changing one property of a gas and seeing how one other property changes with it, which is kind of simple in concept, although the math isn't always simple. Although the math is a lot simpler if you just keep track of what is what. You know, what is the pressure before the change happened? What is the pressure after the change happened? That kind of thing. If you keep that straight, it's a lot easier. There are 4 basic properties of any sample of gas. And those would be pressure, and volume, temperature, and number of particles. We usually use moles to quantify the particles of gas, and lowercase n for number of moles. These are, in fact, interrelated with each other. And in fact, you'll notice that one thing I didn't mention as an important property of a gas sample is the identity of the gas, because it doesn't actually matter for most purposes what the gas is. In physical terms, the relationship between pressure, volume, temperature, and number of particles, or number of moles of particles, it doesn't matter what the gas is. They all behave the same way physically. And so these properties are interrelated with each other. If you change one of them, at least one of the others will change. And that's essentially what the simple gas laws are about. The simple gas laws are about taking any 2 of these variables and changing one of them and seeing how the other one changes, while holding the other 2 constant. So the simple gas laws describe the relationship basically between any two of these properties. For a given sample of gas, if the other properties are kept constant. Okay, so that's assuming we're not changing the other constants. There are several laws, or several simple gas laws. One of them is Boyle's law. And that will be about pressure versus volume when the other two properties, temperature and moles of gas, are not changing. Then there's Charles' law, which is temperature versus volume. And that's when pressure and number of moles is kept constant, are kept constant. There's also Gay-Lussac's law, which is pressure versus temperature when pressure versus temperature when volume and number of moles is constant. And then there's the combined gas law. And that is actually a combination of the three gas laws, you know, as the name implies, combination of these first three gas laws. And that would be how pressure, temperature, and volume all relate to each other if the number of moles of gas is kept constant. And so the combined gas law can actually be used for, in any case that you could use any of these first three gas laws for, and it just might be the case that maybe one of those variables is not changing. But anyway, if you have more than one variable changing and you want to know how the third one responds, then you can use the combined gas law. And then there's Avogadro's law. And that happens to do with volume versus number of moles of gas. And that would be with pressure and temperature constant. And that may, you know, trying to remember all of this all, you know, up at front before we've actually done anything with it seems pretty difficult, but you'll get used to it as we go along and you learn how these quantities relate to each other, because in the end, it really makes sense how they relate to each other. So it's not that hard to remember. So Boyle's law in detail. That's volume versus pressure. And Boyle started out a little over 300 years ago, trying to determine how a volume of a sample of gas changes if its pressure changes, or vice versa, if all the other properties are held constant. Okay, so if you change the pressure, how does the volume change? Or if you change the volume, how does the pressure change? What he discovered was that it was an inverse proportion. And that's assuming, of course, that temperature and number of moles are constant. Because if you start changing the temperature or start changing the number of gas molecules you've got, well, that'll certainly mess up the relationship between volume and pressure. And what this means is that if the pressure goes up, the volume goes down. And it goes down by the same factor. So if you double the pressure, you cut the volume in half. And you can think of that like squeezing a balloon. If you squeeze a balloon, it will, become smaller in volume. And that's because you're compressing the empty space between the gas particles, which is an easy thing to do. If pressure goes down, the volume will go up by, again, the same factor. If you change the volume and you compress the volume, then the pressure goes up by the same factor. So if you cut the volume in half, you've just doubled the pressure. If the volume goes up, the pressure goes down. You've got the same number of particles in a bigger space, so there are fewer collisions between the particles and the walls of the container per unit of time, and that means less total force imparted to the wall over a period of time, and that means less pressure. So in detail, if you decrease the volume, then you have the same number of particles in a smaller space, and they'll collide with the walls more often. So remember, it's force per unit of area. So if you map out a certain area, like a square inch on the wall of the container, and you've decreased the volume of the container, well, there are fewer square inches for the gas particles to collide with, but there are still the same number of gas particles as there were before. So each square inch of that interior wall of the container is going to have more gas particles colliding with it at any given moment. And the gas particles are not hitting any harder than they were before, but there are more of them hitting in any given moment. And that means more pressure in total. On the other hand, if the volume increased, and while you've got more square inches on the inside of the container, but the same number of particles, and that makes for fewer collisions per unit of area of the inside surface of the container. And that means less force per unit of area. And that means lower pressure. This is an important thing to keep in mind when you're diving, underwater, particularly as you're coming up to the surface, because if you make the mistake of holding your breath while you're coming up to the surface, well, the gas that's held in your lungs will be increasing in volume because the pressure on you from the water around you will be decreasing as you get closer to the surface. And so the volume of gas in your lungs will be expanding, and your lungs may not be able to hold that. And well, you'll basically be forced to exhale sooner or later. But if you try to hold the gas in, it can really damage your lungs. So you have to remember to keep breathing as you're coming up to the surface. This law can be used to track changes in a gas over time. Since we know that volume is inversely proportional to pressure, then that means that volume is equal to some constant times 1 over pressure. Or in other words, volume is equal to a constant divided by pressure. Or we can say that pressure times volume is equal to a constant. And for any given sample of gas, that constant will be a different number, but it'll always be that same number for that same sample of gas. Even if you change one of these two properties. So if you change pressure, volume will change, but pressure times volume will still be that same constant. So say pressure times volume before a change, which we'll call P1 times V1, is going to be equal to that constant. And pressure times volume for that same gas sample after a change, which we'll call P2 times V2, will be that same constant. And since P1 times V1 is equal to something, and P2 times V2 is equal to that same thing, that means that they're equal to each other. So Boyle's law is usually expressed as P1 V1 equals P2 V2. That is, pressure times volume for a gas sample before a change will be equal to the pressure times the volume of that same gas sample after a change. So for Boyle's law, we have P1 V1 equals P2 V2, where P1 is original pressure, V1 is original volume, and P2 is new pressure, and V2 is the new volume. And between P1 and V1 and P2 and V2, some sort of change occurred in that sample of gas. Pressure and volume units can be anything you want, but they need to be the same on both sides. So for pressure, you could use atmospheres or pascals or torr or pounds per square inch if you want any of those, but P1 and P2 have to be in the same units. Volume, you could use, again, you could use milliliters or liters or gallons or cubic feet, or whatever you want, as long as they're the V1 and V2 are in the same units. Because you end up solving this equation for whichever of these quantities you don't know. And the units you don't want, or for whatever you're not looking for, will end up canceling out. And you end up with whatever units you started out with for the quantity that you're looking for. So a quick example of something like this would be a snorkeler takes a syringe. I cut out the unimportant parts. A syringe with 16. A syringe is we're calling it a syringe just because it's basically a container for holding gas, where you know how much you've got and where that amount can easily change. So something like a plunger or a syringe with 16 milliliters of air is taken from the surface of the ocean, where the pressure is 1 atmosphere. To an unknown depth, where the volume of the air in the syringe is 7.5 milliliters. What is the pressure? Of the water at the depth. Okay, so we know that our equation is P1 V1 equals P2 V2, and we know that we have to figure out what P1, V1, P2, and V2 are to the best of our abilities, based on what's given in the equation, or in the problem. Let's see, P1 would be the original atmospheric pressure, which is 1 atmosphere. V1 would be the volume at 1 atmosphere, which is 16 milliliters. P2, that's actually the pressure that we're being asked for, so we don't know that. That's the unknown. And V2 would be the volume at that pressure, which is 7.5 milliliters. Okay, so these are the quantities we're going to put in the equation. We're looking for P2, so we solve the equation for P2. We have to get rid of V2 on the right-hand side, and to do that, you just divide both sides by V2. So P1 V1 over V2 should be P2. P1 is 1 atmosphere. V1 is 16 milliliters, and V2, 7.5 milliliters. Notice how milliliters cancel, and you end up with atmospheres as the unit for the answer. If you didn't want the pressure in atmospheres, well, you could just find it in atmospheres and then convert it to whatever units you want. Or alternatively, you could have converted this pressure to the units you wanted, in which case you would get the units you want out of this equation automatically. But anyway, 1 times 16 divided by 7.5 is 2.13 atmospheres. Okay, so that's how you can tell what the new pressure is. So it's pretty simple. And we're over 30 minutes now, so I will go on in part B to Charles' Law.